Something shifted in 2024, and most developers didn't catch it in real time. Addy Osmani, engineering director at Google Chrome, the person who literally shapes how millions of developers think about performance and tooling, published a statement that should have set off alarms across the entire industry. He said the developer's role has permanently shifted from being a coder to being an orchestrator. Not will shift. Not might shift. Permanently shifted. Tense. When someone at that level of Google's engineering leadership uses language like that, it is not a prediction. It is a report from the front line. The question is not whether this transition is happening. The question is whether you've already been left behind by the time you finish watching this lecture. By the end of this chapter, you will understand exactly what that orchestrator role means, why single-agent tools are only the beginning, and what a real multi-agent pipeline actually looks like in production. Now here is where it gets uncomfortable. Most developers who heard AI-assisted immediately went and picked up Claude Code, and honestly, that was the right first move. Those tools are genuinely powerful. But here is the pattern I keep seeing in real teams. You get a massive productivity boost in the first 2 weeks, then you hit a wall. The tasks that still feel hard, coordinating across modules, maintaining consistency between the front-end contract and the back-end implementation, catching integration errors before they compound. None of those get solved by a single agent, no matter how good the model is. The single-agent bottleneck is not about the quality of the AI. It is a structural problem. One context window, one thread of reasoning, one point of failure. And developers who are pulling ahead right now are not the ones with the best prompts. They are the ones who figured out that the ceiling is architectural, not conversational. But wait, if single agents have a hard ceiling, why are most tutorials still teaching you to use them that way? That contradiction is exactly what we are going to unpack next. Let me be direct about what this lecture is actually going to do for you, and what it is not to do. This is not a tutorial on how to use any specific tool. Tools change every 3 months. What I am giving you is a decision framework. By the time we are done, you will be able to look at any feature on your backlog and answer 3 questions with confidence. First, is this feature complex enough to justify splitting across multiple agents? Or will the coordination overhead actually slow you down? Second, if you do split it, what role should each agent own, and where do you draw the boundary between them? Third, what are the specific failure modes you need to anticipate before the agents ever start running? Because in multi-agent systems, failures compound in ways that are much harder to debug than single-agent errors. These are not beginner questions. Senior developers get these wrong. And getting them wrong does not just cost you time, it costs you trust in the entire paradigm, which means you abandon a genuinely powerful approach because you tried it without the right mental model. The orchestrator mindset is a skill. It is learnable. And it starts right here. Here is what the rest of this lecture looks like in concrete terms. We are going to build a real feature, not a toy example, not a hello world, a feature that has enough complexity to actually stress test a multi-agent approach. We will route it through 3 agents with distinct roles. And here is the part most tutorials skip entirely. We are going to deliberately break the coordination layer and watch what happens. Because understanding how multi-agent systems fail is just as important as understanding how they succeed. You cannot develop good orchestration instincts by only seeing the happy path. The failure case in this demo is not a mistake while preparing, it is engineered. I chose it because it represents the exact class of error that kills multi-agent adoption in real teams. They see this failure, they do not understand it, and they conclude that multi-agent coding is immature hype. It is not. The failure is predictable and preventable. Only once you know what to look for. And that is precisely what Chapter 2 is going to show you. Why even AI-assisted solo coding has a hard ceiling that no amount of better prompting can break through. Let's be honest about where we've been. In 2021, Git Copilot shipped and developers lost it. Inline autocomplete felt like magic. But within 6 months, the ceiling was visible. It only knew your current file. Then came chat-based pair programming in 2023. You could paste errors, ask for refactors, have a conversation. Better but still reactive. You drive. The AI responds. Now in 2024 and 2025, we have autonomous agents, tools like Claude Code, Cursor Agent, and Devin that can read your entire repo, write files, run tests, and loop on failures. Each generation looked like the final form. Each generation hit a wall. The question isn't whether AI coding tools are powerful. The question is, why does every single generation eventually stall? The answer is structural, and it has nothing to do with the model's raw intelligence. Stay with me, because the ceiling mechanism we're about to see explains everything that comes later. Here is the core mechanism that nobody talks about clearly enough. A single agent, no matter how good the underlying model, operates inside a context window. Right now that might be 200k tokens, even 1 million tokens on paper. But here is the brutal truth from production usage. Token count is not the real limit. The real limit is reasoning coherence over long sequential chains. When an agent handles a complex task, say refactoring a payment module that touches authentication, database schema, and 3 API layers, it must track all of those dependencies simultaneously while generating code. By the time it reaches file number 4, it has already begun to contradict decisions it made in file number 1. This is context fragmentation. The model isn't getting dumber, it's getting lost in its own history. And sequential reasoning compounds this. Each step depends on the previous step being correct, so errors don't just persist, they multiply. More tokens fix a sequential architecture problem. That's a category error, and that category error is exactly what most developers keep making. Don't take my word for it. Here is what real developers are reporting in the wild. On the Claude Code subreddit, one senior engineer wrote, "It rewrote my auth middleware perfectly. 3 files later, completely forgot it had added a session check and duplicated the logic with a different variable name. Now I have 2 systems fighting each other." On X, a developer posted a cursor thread showing their agent enter a loop. It would fix a TypeScript error, which broke a test, which it then fixed by reverting the original change, which reintroduced the TypeScript error. 8 iterations, 0 net progress. This is not a hallucination problem. This is a structural architecture problem dressed up as a model quality problem. Every time a developer blames the model and tries a different prompt, they are solving the wrong equation. The pattern you're seeing in these complaints, it's not random. It follows a predictable failure mode that we now have a name for, and more importantly, a solution for. Let's find out what that solution looks like structurally. Let's make this concrete with a real task comparison. Imagine you need to build a user notification feature, database schema change, backend service logic, REST API end, and front-end component. With a single agent sequential flow, you prompt the agent on the schema, wait, review, then prompt on the service, wait, review, each step blocked on the previous. The agent holds growing context about all 4 layers simultaneously, and you're context switching mentally between reviewing its output and planning the next prompt. Total elapsed time in practice: 3 to 4 hours for a mid-complexity feature. Now imagine the same feature with parallel agents. One agent owns the database layer, one owns the backend service, one owns the API contract, one owns the front end. They execute simultaneously. An orchestrator, which is now you at a higher level, resolves the interface contracts between them. Total elapsed time, under 90 minutes. But here is the part developers miss. The time saving is almost secondary. The bigger gain is cognitive overhead reduction. When you stop holding every implementation detail in your head and start managing interfaces and outcomes instead, you stop being the bottleneck. And that changes everything about your leverage as a developer. This brings us to the identity shift that most developers resist, and resistance here is expensive. For 20 years, being a great developer meant being a great code author. You were judged by the elegance of your functions, the cleanliness of your abstractions, the speed at which you could write correct code. That identity is now being renegotiated whether you want it to be or not. The new leverage point is not line-by-line authorship. It is task decomposition and agent coordination, which means your valuable skill is now the ability to break a complex problem into coherent subproblems with clean interfaces, assign those subproblems to agents with the right constraints, and synthesize their outputs into a coherent whole. This is the orchestrator role, and it is not easier than writing code. It is different. It requires systems thinking, not just implementation thinking. The developers who thrive in this model are the ones who already thought in components, interfaces, and contracts. The ones who struggled are the ones who built everything as one monolithic context. Which one are you? Because the 3 patterns we'll examine next will make that answer matter a great deal. Let's crystallize what we've established in this chapter, because these points are the foundation for everything that follows. First, the single agent ceiling is not a model quality problem. It is an architectural problem. A better model running in a single sequential thread will still fragment context on large tasks. Prompting harder, using a different system prompt, or switching to a newer model are all solving the wrong variable. Second, context fragmentation follows a predictable pattern. It gets worse as cross-file dependencies increase, and it compounds through sequential error propagation. This is not random. It is a structural property of single-threaded execution. Third, the developer's mental model is the hidden cost. Holding all implementation context in your own head while managing a single agent is what creates the cognitive ceiling on top of the technical ceiling. You have 2 ceilings stacked on top of each other. The implication is clear. If the ceiling is structural, the solution must also be structural. More of the same is not the answer. A different architecture is the answer. So if the ceiling is structural, what is the structural response? Multi-agent orchestration. not as a trend, not as hype, but as the only architectural pattern that directly addresses context fragmentation at scale. When you distribute work across agents with bounded, non-overlapping contexts, you eliminate the fragmentation problem by design. When you coordinate those agents through an orchestrator, you replace the developer's cognitive bottleneck with a systematic coordination layer. But here is where most developers get it wrong again. They treat multi-agent as a single pattern. They spin up a few agents and hope for emergence. What actually works is choosing the right orchestration pattern for the right task type. And there are exactly 3 patterns that cover the vast majority of real engineering scenarios. In the next chapter, we're going to break down all 3, the Subagent pattern, the team pattern, and the hierarchy pattern, and you'll know precisely which one to reach for when. If you've ever spun up multiple agents and watched them produce contradictory outputs, the next chapter is the diagnostic you've been missing. Let's start with the simplest primitive in multi-agent coding, the Subagent pattern. Here's the core idea. You have one orchestrator agent that holds the master plan, and when it hits a bounded, well-defined subtask, it spawns a specialist agent to handle exactly that piece. Nothing more. The orchestrator waits, collects the output, and integrates it back into the main thread. This is single delegation. It looks deceptively simple, which is exactly why most developers underestimate how much precision it requires. The orchestrator isn't just handing off work, it's handing off context, constraints, and an implicit output context. Miss any of those 3, and the Subagent returns something technically correct, but practically useless. Claude Code implements this natively through its task tool, which gives you a structured way to fire off a Subagent with an isolated context window. But here's the thing most tutorials skip. The task tool is only as good as the prompt you feed it. The pattern is the scaffolding. Your prompt engineering is the foundation. And the foundation, what we're going to stress test right now. Now let's get mechanical. This is what a task tool invocation actually looks like in Claude Code. 3 fields decide everything. The description, which tells the Subagent who it is and what domain it owns. The prompt, which is the actual work instruction. And the constraints block, which is where most developers leave money on the table by writing nothing. Look at this code carefully. The description isn't write some tests. It's you are a test engineer. Your sole responsibility is generating PyTest unit tests for the function signatures provided. Do not modify implementation files. That role specificity is doing enormous work. It's preemptively collapsing the search space the Subagent will operate in. The prompt then gives concrete input. The function signatures, the expected behavior specifications, and critically, the output format, markdown, raw Python file, you must state it. The constraints field is your circuit breaker. Max file count, forbidden directories, no work calls. Every constraint you skip is a degree of freedom you're handing to a system that has no intuition about your production environment. Developers who skip constraints are the ones filing bug reports about agents that went rogue. They didn't go rogue. You just didn't build the fence. The real test of a good delegation prompt is whether a new hire could follow it without asking you a single clarifying question. Even with a solid task tool setup, 2 failure modes will find you if you're not explicitly defending against them. The first is scope creep. The Subagent decides your request implies adjacent work. It refactors the function it was testing, adds a logging it thought would be helpful, touches files you never mentioned. This isn't the agent being malicious. It's the agent being helpful in the worst possible way. The fix is ruthless constraint specificity. What files can be touched? What files are off limits? What the agent is explicitly not responsible for. Write the negative space, not just the positive task. The second failure mode is output integration mismatch. The orchestrator expects a JSON object with a specific schema. The Subagent returns a markdown code block with commentary. Now your orchestrator's parser throws an exception, your entire pipeline halts, and you spend 40 minutes debugging what is fundamentally a handshake failure. These 2 failure modes compound each other in team and hierarchy patterns, which is exactly why we're naming them here at the simplest level. If you can't control a single Subagent delegation, you have no business running 5 agents in parallel. Up next, that's exactly what we're going to attempt. Now we step up in complexity. The agent team pattern takes the Subagent primitive and runs multiple instances simultaneously, not sequentially. This is the fan-out fan-in model. A coordinator agent fans out a large task into n independent subtasks, fires n specialist agents in parallel, waits for all n to complete, then fans back in to merge and reconcile their outputs into a coherent whole. The performance argument for this pattern is obvious. Parallelism compresses wall clock time dramatically. What took a sequential agent 40 minutes can theoretically finish in 10. That's the promise. But here's the critical word in that last sentence: independent. The fan-out only delivers its speed advantage when subtasks are genuinely independent, meaning Agent A's output does not need to be an input to Agent B's work during execution. The moment you have a dependency between parallel agents, You've broken the pattern's core assumption, and you're now dealing with a coordination problem that most teams discover only after they've already built the pipeline. The coordinator's job isn't just task distribution, it's task decomposition into truly independent units. That decomposition skill is the difference between a team pattern that accelerates you and one that creates a debugging nightmare. And the debugging nightmare has a specific name: output reconciliation failure. Let's make the team pattern's main risk concrete with a direct comparison. On the left, well-defined agent role boundaries. Agent A owns the database schema. Agent B owns the API handler logic. Agent C owns the test suite. These three domains have a clear interface contract. Agent B knows the schema shape Agent A will produce, because the coordinator specified it upfront before fan-out. Agent C knows the endpoint signatures, because those were also specified upfront. Nobody is guessing. On the right, poorly defined roles. Agent A is told to handle the backend. Agent B is told to write the API. Agent C is told to make sure it works. Now you have three agents who all think they own the data model. Two of them will generate conflicting schemas. The coordinator then faces an output conflict that isn't a simple merge. It's an architectural decision requiring human judgment. And here's the brutal part. This conflict is harder to debug than any single agent bug, because the error doesn't appear at generation time. It appears at integration time, when you're trying to reconcile two valid-looking but mutually incompatible outputs. The rule is simple. If two agents could plausibly claim ownership of the same artifact, your role definitions have failed before the agents even start running. Let's ground this in a real scenario. You're building a REST API feature, a new user preferences endpoint. Three agents, cleanly split. Agent 1 is the schema agent. It owns the database migration, the pedantic models, and the JSON response schema. Its output is a schema specification document, nothing else. Agent 2 is the implementation agent. It receives that schema spec as input and owns the FastAPI route handler, the service layer logic, and the database query. It writes to exactly those files, nothing else. Agent 3 is the test agent. It receives both the schema spec and the endpoint signature document and generates PyTest integration tests. It writes to the tests directory only. Notice what makes this work. The interface contracts, schema spec and endpoint signature document, are defined by the coordinator before any agent fires. Agent 2 and 3 are not guessing at Agent 1's out format. They're consuming a pre-specified contract. This is the discipline that separates a team pattern that ships from one that burns an afternoon of debugging. But here's what this table doesn't show. What happens when one's schema has a bug that Agent 2 builds on top of? That's the failure mode, and trigger live in the next chapter. The third pattern is the most powerful and the most dangerous: hierarchical delegation. This is where multiple agents operate across multiple layers of authority, with orchestrators at higher tiers delegating to executors at lower tiers, who may themselves delegate further down. Addy Osmani, one of the clearest thinkers in this space right now, has mapped current tool ecosystem into a three-tier taxonomy that gives us a useful framework for thinking about hierarchy. Tier 1 tools are primary orchestrators. They hold the broadest context, make architectural decisions, and coordinate across the entire codebase. Think Claude Code in agent mode or GitHub Copilot workspace. Tier 2 tools are specialist executors. They receive a bounded mandate from a Tier 1 orchestrator and execute with domain expertise. Cursor in composer mode, for instance, excels here. Tier 3 tools are narrow task utilities. Linters, formatters, test runners, code generators for specific patterns. They do one thing, they do it well, and they should never be making architectural decisions. The hierarchy maps authority to tier level. The closer to Tier 3, the less autonomy an agent should have, and critically, the less blast radius when it fails. And blast radius is the variable most developers forget to calculate before they wire up their pipeline. Let's put specific tools on the tier map with honest assessments, because the marketing copy for every one of these tools claims it can do everything, and that's exactly the kind of hype we need to cut through. Claude Code in agent mode earns its Tier 1 placement when you need cross-file reasoning, multi-step planning, and tool orchestration. Its authority should end at production infrastructure changes. You do not want an LLM agent with unreviewed access to your CI/CD pipeline or cloud credentials. Cursor in composer mode is genuinely excellent as a Tier 2 executor for focused implementation tasks inside a defined scope, where its authority should end. Anything requiring awareness of how the current file interacts with the broader system architecture. GitHub Copilot Workspace sits awkwardly between Tier 1 and Tier 2 as the interface of a planner, but the context limitations of an executor. Use it for scoped feature work, not for system-wide refactoring. The honest note on all three: none of these tools have a reliable mechanism for knowing when they've exceeded their competence boundary. That judgment still lives with you. The tier system isn't about what the tools claim. It's about where you, as the architect of the pipeline, choose to hard stop their authority. That decision is non-delegatable. So when do you use which pattern? Here's a decision rule with 3 variables. First, task independence. Can this work be cleanly split into subtasks that have 0 runtime dependency on each other? If yes, you're a candidate for the team pattern. If no, if tasks must hand off to each other, you're in Subagent or hierarchy territory. Second, output coupling. How tightly must the agent's outputs fit together? Loose coupling, like separate documentation and separate test files, tolerates the team pattern's reconciliation step. Tight coupling, like a schema that must match an implementation, that must match a test fixture, demands the hierarchy pattern where contracts flow downward through tiers before any agent fires. Third, and most important, what's your tolerable failure blast radius? A subagent failure is contained. One subtask fails, one piece of output needs regeneration. A team pattern failure can corrupt and output simultaneously if the role definitions were wrong. A hierarchy failure can cascade through tiers, with Tier 2 agents building confidently on a flawed Tier 1 decision for minutes before anyone detects the divergence. Start with the pattern that has the smallest blast radius you can afford for the task at hand. Escalate to higher complexity only when you have observability into what the lower complexity pattern is doing. In the next chapter, we're going to prove why that last sentence matters by deliberately breaking all 3 patterns on a live feature. Here's where most developers make their first mistake with multi-agent systems. They skip the contract phase and jump straight to invocation. We're building a user authentication module with rate limiting. Simple enough to fit in 1 agent, complex enough to stress test 3. Before a single agent is invoked, we define explicit input-output contracts for each role. Agent 1 owns the data schema and an API surface. Agent 2 owns implementation only. It cannot touch schema. 3 owns test generation, consuming Agent 1's output as its sole source of truth. Notice what's happening here. We're spending deliberate engineering time before any token is consumed. That upfront cost is exactly where most orchestration attempts collapse. They skip this step entirely. The contracts aren't suggestions. They are hard boundaries. And in about 2 minutes, you'll see exactly what happens when one agent decides to ignore them. Let's invoke Agent 1 live. Watch the prompt structure carefully. This is not a casual chat message. We're using Claude Code's task tool, which lets the orchestrator spawn a subagent with explicit role constraints baked into the system prompt. The key elements you're seeing here: a role declaration that explicitly states what Agent 1 cannot do, no implementation, no test, a scope boundary that limits output to TypeScript interfaces and the Redis schema, and a structured output requirement that forces JSON serializable contracts, not prose. Why does structured output matter? Because Agent 2 and Agent 3 will parse this programmatically. Ambiguity in Agent 1's output becomes a cascading failure across every downstream agent. Notice the token budget is also constrained. We're not giving Agent 1 infinite context. Focused agents with tight constraints constantly outperform broad agents with open-ended prompts. That's not intuition. That's what the benchmarks show. Watch what Agent 1 returns, and then we'll fan out to the next 2 agents simultaneously. Agent 1 has returned its schema. We now have a shared context artifact, a JSON object containing TypeScript interfaces for the auth token, the rate limit record, and the Redis key naming convention. This becomes the single source of truth that both Agent 2 and Agent 3 consume. Now the fan out. We dispatch Agent 2 and Agent 3 in parallel, each receiving Agent 1's output as a read-only input parameter. Agent 2 begins implementing the Express middleware and Redis integration. Agent 3 simultaneously generates just test cases based purely on the schema contracts. This parallel execution is the compelling part. Theoretically, we've compressed what would be sequential work into concurrent work. But here's the question you should already be asking yourself. What happens if Agent 2 decides the schema needs a small adjustment mid-implementation? That's not a hypothetical edge case. That's the most common failure mode in production multi-agent pipelines, and we're about to reproduce it deliberately. First, let's see what the happy path actually looks like, because you need to know what you're targeting before you can diagnose why it broke. In the successful run, Agent 2's implementation exports exactly the types defined in Agent 1's schema. The rate limit record interface is consumed without modification. The Redis key format matches the naming convention Agent 1 specified. Agent 3's tests import the same TypeScript interfaces and write assertions against the exact method signatures Agent 2 implemented. When the orchestrator merges these outputs, there are 0 conflicts. The integration test suite passes on first execution. This is clean multi-agent coordination. Each agent operated within its declared boundary, and the contracts did the integration work automatically. The orchestrator review step becomes nearly trivial. Diff the output types against the input schema, confirm no mutations, ship. This is the benchmark. Clean contracts eliminate the merge negotiation that kills so much multi-agent work. But now let's break it. intentionally, in the most realistic way possible. Now the failure. And this is deliberate. We're reproducing the single most common multi-agent breakdown in real code bases. Midway through implementation, Agent 2 determines that Agent 1's rate limit record interface is missing a field. It needs a window reset timestamp for the HTTP response header. Reasonable engineering decision. Agent 2 adds the field locally and continues implementation. It does not signal the orchestrator, does not update Agent 1's schema artifact. Agent 3, running in parallel, has no visibility into this mutation. Agent 3's tests are written against the original schema, the one without window reset. Both agents complete. Both report success. The orchestrator merges the outputs. The tests run. And here is where it gets genuinely dangerous. Tests don't loudly fail with a type error. Instead, assertions pass on the fields they know about, and the missing timestamp goes untested entirely. The feature ships with an unvalidated contract. This is not a hypothetical failure mode. This is what scope creep looks like inside a multi-agent system, and it's silent. How do you diagnose this live? Step 1. Diff Agent 2's output types against Agent 1's locked schema artifact. That's where the divergence surfaces. A field present in the implementation but absent from the contract. Step 2. Cross-reference Agent 3's test coverage against the implementation's actual interface, not schema. Coverage gaps on implementations that aren't in the original schema are your signal. Step 3, and this is critical, ask why Agent 3's tests passed without objection. Silent passing is more dangerous than a loud failure because it creates false confidence. The minimal fix protocol here is not to rerun all 3 agents. It's targeted, update the schema artifact, re-invoke Agent 3 only with the corrected schema, rerun the test suite. The implementation doesn't need to change. The key lesson is that multi-agent debugging requires sync artifact lineage. Agent touched which contract and when. Without that audit trail, you're debugging a distributed system with no logs. Coming up next, we put actual numbers on all of this and ask the question nobody wants to answer. Did 3 agents actually save time, or did they just redistribute the cost? Let's put real numbers on what just happened. Because the narrative around multi-agent systems is almost always about speed gains, and the actual wall clock data from this demo tells a more complicated story. Single agent run on the same feature, JWT auth with rate limiting, came in at 4 minutes 20 seconds, end to end, with no orchestration overhead. The 3-agent orchestration run, including contract definition time, parallel execution, and the successful merge, 6 minutes 10 seconds. That is nearly 2 minutes slower in the happy path. Factor in the failure scenario, the scope creep detection and targeted re-invocation, and total time reached 9 minutes 40 seconds. Now, single-agent output quality scored lower on test coverage granularity. The 3-agent system produced more comprehensive test cases because Agent 3 had dedicated focus. But you need to decide, is that quality delta worth a 40 to 120% per time increase? For a one-off feature, probably not. For a recurring pattern you'll reuse across a codebase, the calculus changes entirely. Here's the uncomfortable truth the benchmark doesn't show you. Multi-agent orchestration doesn't eliminate cognitive load, it relocates it. In a single-agent workflow, your mental energy goes into writing code and reviewing its output. In a 3-agent orchestration, that same energy goes into writing contracts, designing agent boundaries, and debugging coordination failures. That is not inherently better. It's only better if your contracts are more precise than your code would have been. Think about what that means practically. If you're a developer who writes vague prompts, multi-agent orchestration will multiply your vagueness across 3 agents simultaneously. The prompt engineering cost for the contract phase in this demo was approximately 25 minutes of careful thinking before a single token was consumed. For a 4-minute task, that's a 6-to-1 investment ratio on the setup alone. When does that ratio flip in your favor? When the same contract structure is reused across dozens of similar features. When the parallelism is real, not simulated with sequential agents. And when the quality bar requires specialization that a single context window genuinely cannot deliver. But that's a much narrower use case than most tutorials admit. One takeaway from this entire demo, and it's the one that will save you the most time in the next 6 months. The quality of your task decomposition determines whether multi-agent coding multiplies your output or multiplies your confusion. That's not a soft principle, we just measured it. The 25 minutes spent on precise contracts produced a clean integration. The moment one agent skipped the contract, burned 5 additional minutes on diagnosis alone. Multi-agent orchestration is not a productivity shortcut. It is a software architecture decision that demands the same rigor you'd apply to designing a microservices boundary or a database schema. Treat it casually, and you get distributed failure with extra steps. Treat it with precision, and you get genuine parallelism and specialization that a single context window cannot replicate. Now here's what we haven't talked about yet, There are entire categories of tasks where you should never use multi-agent orchestration, regardless of how well you design your contracts. That's the next chapter, and the conditions that disqualify a task are not what most developers expect. We just watched 3 agents fail on a single feature. But here's the uncomfortable question nobody asks before spinning up a multi-agent pipeline. What is the actual cost of orchestration itself? Every agent invocation carries fixed overhead, context loading, prompt construction, API round trips, and token burn just to coordinate. With Claude Code pricing as a reference point, a single orchestration handoff can consume anywhere from 2,000 to 8,000 tokens before a single line of useful code is written. That means if your task is small, a one-file refactor, a quick type fix, a single test case, you are paying a coordination tax that dwarfs the actual work. The threshold is roughly this. If a single skilled agent can complete the task in under 3 tool calls, orchestration is almost certainly the wrong choice. The break-even point only appears when tasks are genuinely parallelizable and independent. Everything below that threshold is just expensive theater. But knowing the threshold exists is only half the problem. The real danger is the 3 patterns that make developers cross it without realizing it. Now let's name the 3 anti-patterns explicitly, because I see them in almost every team that adopts multi-agent workflows too early. Anti-pattern 1, orchestrating tightly coupled tasks. If Agent A's output is the direct input to Agent B with no transformation or branching in, you don't have 2 agents, you have 1 agent with an expensive telephone call in the middle. Anti-pattern 2, spawning agents without interface contracts. This is what killed the demo in the last chapter. When agents share a file system or a shared memory context, without explicit schemas for what they write and read, you get silent data corruption that is nearly impossible to debug. Anti-pattern 3, using a hierarchical orchestrator where a simple subagent loop suffice. Hierarchy adds cognitive load, adds failure surfaces, and adds cost. If you can express the workflow as a linear sequence with 1 decision point, a flat subagent pattern beats a tree every single time. These 3 patterns share a common root. The developer reached for orchestration because it felt powerful, not because the problem required it. And that feeling, that is the real trap. So what does the community actually say when they fall into it? The community data confirms this at scale. On the Cursor Discord and VI engineering forums in early 2025, a recurring pattern emerged among developers who publicly documented reverting from multi-agent setups back to single-agent or even plain LLM calls. The through line in their postmortems is remarkably consistent. One developer with over 200 upvotes wrote, "I spent 2 weeks building an orchestration layer that a single Claude session with good prompting replaced in an afternoon." Another from a YC-backed startup, "Our agent pipeline had 4 nodes. 3 existed to fix mistakes the first one made. That's not orchestration, that's a bug with extra steps." The pattern behind these failures is not that multi-agent systems are wrong. It is that developers had orchestration as a solution before they fully understood what was failing in their single-agent setup. You cannot orchestrate your way out of a bad prompt or a poorly scoped task. And this brings us to the most important slide in this entire chapter, a decision framework that tells you exactly when to orchestrate and when to stop. Here is the decision matrix I use before recommending multi-agent architecture to any team. 4 criteria, each scored from 3. First, task independence. Can each subtask be completed with 0 knowledge of what another agent is currently doing? Score 1 if they share state, score 3 if they are fully independent. Second, output coupling. Does Agent A's output format need exactly match Agent B's expected input? High coupling, score 1. Loose coupling with a schema buffer, score 3. Third, blast radius of failure. If one agent produces garbage output, how much of the final deliverable is corrupted? If the answer is all of it, score 1. If failure is isolated and recoverable, score 3. Fourth, team familiarity with agent debugging. This is the one teams always underestimate. Debugging a multi-agent failure requires reading interleave tool call logs across multiple context windows simultaneously. If your team has never debugged a single agent loop failure, end score 1. Add up the scores. Below 8, do not orchestrate yet. 8 to 10, proceed with a pilot on a non-critical path. You're ready. And here is the part that will surprise you. Most teams score below 8 on their first honest assessment. Let me close the reality check with the most important framing of this entire lecture. Multi-agent coding is a force multiplier, but force multipliers only work if there is already a force to multiply. If you cannot reliably get a single agent to complete a scoped task end-to-end, adding a second or third agent does not fix that. It amplifies the failure. The prerequisite skill is not orchestration knowledge, it is single-agent failure mode literacy. You need to know why an agent hallucinates a file path, why it overtruncates context, why it misinterprets an ambiguous instruction. Until you can diagnose those failures consistently, every orchestration layout is just another place for those failures to hide. The real trap in multi-agent adoption is not the technology, it is skipping the foundation and trying to build the cathedral on sand. Master the single agent first. Then and only then does orchestration become a genuine multiplier rather than an expensive distraction. Coming up next, your actual starter move, a minimal, reversible first orchestration pattern you can ship this week without burning your codebase. So where is this ecosystem actually heading over the next 12 months? Because the tooling landscape matters, it determines which skills compound in value and which become obsolete. Based on current trajectory, in the near term, through mid-2025, we're seeing standardization pressure on agent communication protocols. OpenAI's Agents SDK, Anthropic's Claude Code tooling, and Google's Gemini function calling are all converging toward a shared interface pattern, which means the interface contract skills you build today will transfer. By late 2025, expect native agent checkpointing and rollback to become a first-class feature in at least 2 major platforms, which directly reduces the blast radius problem we scored in the matrix. And by 2026, agent observability tooling, think distributed tracing, but for LLM tool calls, will as standardized as application performance monitoring is today. The developers who will have the highest leverage in that future are not the ones who orchestrated the most agents. They are the ones who understood failure modes deeply enough to design resilient patterns from the start. That foundation is exactly what the next chapter gives you, your first concrete, low-risk orchestration move that you can deploy this week. We've spent this entire lecture diagnosing the trap. Now let's talk about the exit. Before you spin up a single agent for your next feature, you need to run exactly 3 decisions, not 5, not 10. 3. Is this task independent enough? Meaning, can 2 agents work on different parts without constantly reading each other's intermediate state? If the answer is no, you don't have a parallelizable task. You have a sequential pipeline pretending to be one. Second, can you write the interface contract in 3 sentences or fewer? If you need a paragraph to describe what agent A hands off to agent B, the boundary is wrong. Third, what is the failure blast radius? If agent B silently produces garbage and agent A never finds out, how much of your codebase is corrupted before a human catches it? These 3 questions are your pre-flight checklist. Skip any one of them and you're not orchestrating, you're just adding complexity. Run all 3 cleanly, and you have a green light. But passing the checklist is only the beginning. The real question is where you actually start. So you've passed the checklist. Now here's the lowest risk entry point I recommend to every senior developer making their first real orchestration move in a production base. The 2-agent test generation split. Here's the pattern. Agent 1 reads your existing function and generates test cases, edge cases, boundary conditions, the full matrix. Agent 2 takes those test cases and writes the actual test code. These 2 tasks are naturally independent. The interface contract is trivially clear. Agent 1 outputs a structured list of test scenarios. Agent 2 consumes that list and produces runnable code. The blast radius if Agent 2 fails? Your CI pipeline catches it immediately. No production code is ever touched. This is minimum viable orchestration. You build 2 things simultaneously. A useful artifact for your codebase and the muscle memory of defining contracts, handling agent output validation, and debugging inter-agent handoffs in a safe environment. Once you've done this once on a real feature, the mental model clicks. You stop thinking in terms of which AI tool do I use and start thinking in terms of where is the right boundary. That shift, from tool user to system designer, is exactly what separates developers who scale with AI from those who get replaced by it. And that brings us to the final verdict you've been waiting for. Here is the final verdict, stated without hedging. The orchestrator mental model is not optional for developers who want to remain high leverage as model capability continues to scale. This is not about hype. Look at what's already in production. Engineering teams at major tech companies are running multi-agent pipelines for code review, dependency upgrades, incident post-merge generation, right now, in 25. The benchmark trajectory on reasoning models is not flattening. Individual agent capability is going up every quarter. That means the value of a developer who can only prompt a single agent is going down at the same rate. The developers who stay indispensable are the ones who design the systems those agents run inside, who define the contracts, set the guardrails, interpret the outputs, and make the architectural calls that agents cannot make. That role is the orchestrator. The question is not whether you need to develop this skill. The question is only timing. Do you build it now on a low-stakes test generation task, or do you build it under pressure when your team's roadmap depends on it? The trap most developers fall into is waiting until the pressure is already there. Now you know how to start before it arrives. But even if you start today, there is one problem that no orchestration framework has cleanly solved yet. And it's going to hit you the moment your agents need to remember anything across sessions. You now have the full framework, the trap, the decision criteria, the red flags, the reality check, and the starter move. But I want to leave you with the one open problem that every multi-agent coding system eventually crashes into: persistent agent memory across sessions. Right now, every agent you spin up starts with a blank context window. It has no memory of the refactoring decision you made last Tuesday, no memory of the architectural constraint you documented sprint, no memory of why you rejected the approach it's about to suggest again. This is not a minor inconvenience. This is the reason that multi-agent systems today are mostly stateless, mostly single session, and mostly narrow in scope. The moment you try to run a long horizon coding agent, one that works on a feature over days, not minutes, you hit this wall. The next video goes directly at this problem. We'll look at how teams are approaching agent memory today, vector stores, episodic memory layers, and the emerging pattern of memory-augmented orchestrators. If you're serious about building with multi-agent systems beyond toy demos, that is the next piece of the puzzle you cannot afford to skip. Subscribe, and I'll see you there.